Konnichiwa. Hello, everyone. It's an honor to be here, and thanks to the organizers for having me. Also, thanks for you guys for coming to this talk. My name is HyunWoo Lee, and I'm an Android and React Native developer at Viva Republica, a Korean company that operates Toast, the most popular financial app in South Korea. Additionally, I'm the organizer of the quarterly user group Seoul in South Korea. Today, I'll be telling some essential knowledge that will be highly beneficial as we delve into declarative UI. There's so much to discuss about declarative UI, but in this talk, I'll focus on what declarative UI truly is and how it differs from traditional imperative UI, the common elements that make up declarative UI frameworks or libraries, and finally, the next methodologies for state management. So, let's start with this question. What is declarative UI? Or to put it another way, what does the term declarative actually means? To explain this more clearly, let me give you a simple example. When you first learned programming, you probably wrote simple programs that like this, sums the number from 1 to 10. At the time, both you guys and I would have likely used the loop statement to write the program like over this. But once you start learning about collection functions in Java or Kotlin, you might write your code using the sum function, as you can see. I'm not sure, but from my perspective, it is more simpler than before. Then, what's the difference? Between both those statements you are currently looking at is the best explanation of the differences between examples as we saw. The first example focused on how I can get the sum of elements, while the second simply used the sum function that returns the sum of the list. Although the sum function internally uses a loop, the key point is that you don't need to know about its internal implementation when using it. Using functions like sum or count allows us to focus on what we want to find out. As you might guess, what I've said so far pertains to the imperative and declarative paradigms. In a declarative approach, developers express their intentions through code rather than focusing on the algorithms they need. Declarative UI works in the same way. Like the traditional method, where you had to meticulously describe how to use data to create a single screen, declarative UI focuses on how components on the screen are composed using data. This paradigm is not limited to the single OS or library, but it's a new trend adopted by multiple operating systems or libraries. On Android, it's a Jetpack Compose. On iOS, it's SwiftUI. And in the web ecosystem, React-like libraries are adopting a declarative paradigm to draw UIs. Now, let's see how the common aspects of declarative UI are implemented across various libraries and frameworks. First and foremost, we'll focus on the UI. Since declarative UI is a concept used to create user interfaces, it is crucial to understand what aspects should be considered when building a UI. One crucial point to remember when creating a UI is that a single screen can be composed of multiple components. Those experienced in view-based Android development might recall the challenges of creating custom views or directly drawing canvas and writing unmeasured logic. However, in the declarative UI paradigm, you can create UI components by assembling necessary elements within the view. Then, let's examine how this is implemented across different libraries by looking at an example of the timetable item component in DroidKaigi app. Since understanding can be faster, when we start with the most familiar aspects, we'll first examine the implementation in Android. I appreciate your understanding that the code is written in a very simplified form to grasp the concepts of components. First, what stands out is that functions like text, like section title are being called in within the timetable item component. For those who are intuitive, you might grasp this immediately. Each of these functions renders the text and the like icon and the presentation title on the current screen. Wait a minute. In SwiftUI, you can implement this screen in a similar way to what you see now. ちょっと待って. Although there are some slight differences, the use of components such as the text, like, and section title is almost identical to that in Compose. Also in React Native, a mobile UI library that's based on React, you can also see components such as text, like, and section title being used to construct a single component. As we move through the slides, you may have noticed that each OS implements its declarative UI library in slightly different ways. In Compose and React, components can be created using functions, and SwiftUI can still use structs or classes to create components. And although in the past, React also allowed components to be created using class. In the case of functional components, since there is no constructor, data is received through parameters or defined as local variables within the function. For class-based components, data is passed through constructors or defined in class member variables. Due to time constraints, I will quickly touch on some essential topics for creating components that we won't have time to cover in depth. These are vital components to know, the vital concepts to know when building UIs with declarative UI libraries. So please make sure to familiarize yourself with them. Focusing a bit more on styling, in declarative UI libraries other than SwiftUI, you'll find that components are arranged using the CSS flex concept. If we were to find a similar concept in Android, it will be akin to combining the weight feature of linear layout and within the chain concept of constraint layout. Understanding this aspect of component styling will help you grasp more quickly how views are rendered on the screen. So far, we've discussed how to arrange components on the screen. But will the screens we design always be this simple? For example, in the timetable item component I showed earlier, the shape of heart icon should change when the icon is pressed. How should this be implemented in a declarative UI? In a declarative UI, the concept of state is used to update the screen status. This updating process, often referred to as re-rendering, is commonly addressed by many UI libraries. While the specs can vary due to differences in runtime environments, the terminology and methods used are quite similar. Now, let's take a closer look at how state and re-rendering are handled in different libraries. We saw the timetable item earlier, and now I will add some code to change the state of the like icon. Oh, there has a slight change in the code. And let's focus on these changes. The most noticeable feature is the light state property. In Compose, states are distinguished into mutable state, which allows change to the state's value, and state, which does not. Since we need to change the state of like icon, we must use mutable state. Oh, wait a minute. While mutable state is typically assessed using a delegated property, if you choose not to use this and instead directly handle the mutable state object, you can perform this scripting to separate the values into its like and set its like. Its like represents the value, and set its like is used to change it. This suggests that the Compose runtime uses Kotlin's delegate properties to provide syntactic sugar. And React also changes states in a similar way to Compose. Actually, it will be more accurate to say that Compose adopts the same method as React. In the React ecosystem, useState is used to create state variables and can change the screen. Just like in Compose, its like is used as the value, and set its like serves as the handler to modify the value. However, SwiftUI uses a slightly different method for handling state. Instead of changing the variable itself, you can attach a state annotation to the variable that will alter the screen. In Swift, this is technically called a macro or property wrapper. But since most of you are Android developers, I will use a more familiar term. Only variables annotated with this state can change the view within SwiftUI. If a child view needs to modify its own state using this variable, it attaches a binding macro to the member variable, which tells to SwiftUI to use the externally provided variable to update its own content view. The core of the re-rendering mechanism can be considered largely similar across different systems. The most significant change is that the responsibility for updating screen has shifted from the developer to the system. Previously, developers had to manually set the state or state handlers with the method like, set text or set on-click listener. But in declarative UI frameworks, merely changing state can automatically trigger screen updates. This reduces the likelihood of human errors and providing a significant advantage. While the re-rendering mechanisms across different operating systems share similarities, there are subtle differences. For example, Jetpack Compose uses a process known as smart recomposition, which allows only the necessary parts of the screen to be redrawn as needed. This concept is somewhat similar to React's virtual DOM. The virtual DOM operates by creating a virtual representation of the actual DOM tree on the web page and identifying changes and then re-rendering only the altered parts. In SwiftUI, Different IDs are assigned to subviews within the content view and to subviews extract into structs. Elements with the same IDs are grouped together and screen updates according to change in their state. Okay, let's think a bit deeper. Imagine that when you press the like button, a toast or snack bar pops up saying that the session has been saved. But you'll notice that managing notifications as part of a single screen state is not so simple. Notifications can appear across multiple screens, and ultimately, they serve as a one-time message informing the user of the result of an action. Such logic is not about rendering the screen itself, but rather about performing the necessary tasks to ensure the screen is displayed correctly. In Declarative UI, this type of logic is referred to as a side effect. Examples of side effects you may be familiar with include like HTTP request, permission request, and as I said, notifications. You are probably sick of seeing this component by now, right? We've been using the timetable item component as an example for a while. So now let's add some logic to display a notification based on whether its like is true or not. Okay, now I've added a simple logic to display a toast message. In Jetpack Compose, such side effects can be handled using a launched effect. Also, there are so many side effects handler in Jetpack Compose. Before explaining this, let's see React 1. In React, there's so much famous side effect handler called useEffect. useEffect can take a total of 2 parameters. The side effects are defined within the callback function provided as the first parameter. Okay, let's take a closer look at the useEffect. The second parameter passed into useEffect is called the dependency array. How useEffect behaves depends on the values inside the dependency array. First, when an empty array is passed, the callback function will only run once when the component renders or component mounts. Technically, it might run twice due to React's internal workings, but for the sake of simplicity, it's easier to understand of it as running just once. Second, if the array contains values, the callback function will run whenever one of those values changes. Typically, state values are included in the dependency array. This means that every time the state changes, the side effect is triggered. Finally, if no array is provided, the callback function will run on every re-render. Since this behavior is generally inefficient, it's usually reserved for specific use cases. But there's only one thing left. What if we want to trigger a side effect when the screen is dismissed or the component is unmounted? A cleanup function is executed when the component is unmounted from the screen. This is done by defining the cleanup function as another callback function inside the main callback. Now, shifting back to Jetpack Compose, let's take a look at the use cases for these functions. Launched effect is a handler that manages side effects based on the key value. These key parameters, similarly to dependency array in useEffect. However, if you want the side effect trigger when the component is mounted, you need to pass unchanging values like unit or true as the key. The side effect callback behaves in the same way as the callback in useEffect. Since the callback in the launcher effect is defined as a suspended function, this handler is ideal when you want to handle side effects using toolkits. For example, HTTP request is good in this callback. Disposable effect is a handler as similar as launched effect. There are some key differences between two handlers. The first difference is that the side effect function in disposable effect is not a suspend. As a result, only non-suspend functions can be executed inside it. Secondly, within disposable effect, there is an on-dispose callback that is triggered when the component is unmounted. You can use this callback to handle any logic that needs to be executed when the screen or component is unmounted. And finally, side effect is here. The handler behaves in the same way as useEffect without the dependency array. In other words, the side effect defined here will be triggered on every recomposition. While this can be useful in certain situations, improper use may lead to performance issues, so it's very important to use it with caution. Now, we've covered the essential side effect handlers in Android. Due to time constraints, I couldn't introduce more, and I appreciate your understanding. There are also useful side effect handlers such as remember toolkit scope, or produce state, or etc. So I encourage you to explore them as you continue learning about declarative UI in Android. SwiftUI has also similar side effect handlers. In SwiftUI, side effect functions are directly chained to the component. Now, do you have rough understanding of what each function does? OnAppear triggers when the component appears on the screen. OnDisappear when it disappears, and onChange is executed when the value specified by off-parameter changes. The declarative UI libraries we commonly use handle side effects in a very similar way. What do you think? Isn't it fascinating? I think it's so fascinating. So far, we've covered the state and side effects. In my opinion, understanding this much should be enough to implement basic components or screens. Of course, prior knowledge of the language for handling declarative UI is essential. However, if you ask whether this is enough, I would say no. The applications we build are meant to solve real user problems. And as those situations accumulate, the complexity increases. If the logic continues to pile up and the states keep accumulating without proper refactoring, you will eventually reach a point where development becomes increasingly difficult. Now, let's look at an example of when these technical challenges might arise. Imagine a screen with multiple component layers, like this. And these various components are intertwined in parent-child relationships. Sharing data between them can become quite cumbersome. For instance, how can we efficiently share theme colors or font systems across all those used throughout the screen? The first solution that comes to mind is passing data through parameters or constructors. This approach is commonly referred as prop drilling. The biggest advantage of this method is that it clearly shows which data is passed down to chat components. It can be making easier to debug when errors occur. However, having to pass parameters through every component that uses the data can become repetitive and tedious. And it may negatively affect the readability of the code. The solution to this problem is local scope data. This allows you to easily provide data to all UI nodes, regardless of the depth of the UI tree. In Android, this is referred to as composition local. Depending on how you use composition local, there are two distinct types. The first type is static composition local of, which is designed under the assumption that the provided values will rarely or never change. If the value does change, it triggers a recomposition across an entire screen. The second type is composition local of. A likely static composition local of, when the provided value changes, it only triggers recomposition in the components that are reading the value. On platforms other than Android, this functionality can be simplified into a single usage pattern. In SwiftUI, it is called environment values, and in React, it is known as context. Now, let's briefly go over how to use this feature in each library. Starting with Android, when using composition local, you declare a composition local object by using either composition local of static composition local of. It's common practice to prefix variable name with local, so please keep in mind. In a trailing lambda, you define a default value that will be used when no value is provided. In my case, I chose to set a value that triggers an error. Next, through composition local provider, you can declare what value should be provided through composition local. The first parameter of composition local provider is a var arg, so you can declare as many values as you need. Only the components within the trailing lambda scope can access the values provided by the composition local. If you want to use provided values, just use composition local's correct property. Like this. In SwiftUI, environment values usage is also same as composition local. First, we define a key for environment values by conforming to the environment key protocol. Next, we extend environment values to include our custom environment value. In this code, you'll notice that the variable is dark mode, so serves as an entry point to assess the value associated with the key. As you can see here, you simply provide and use environment values. Okay. In the view that consumes environment values, you use the environment property wrapper to define the entry point for the external environment values. On the providing side, you can decide which value to associate with which key by using environment function. The usage of context is almost identical. As you can see from the code, creating a context object and setting up a provider to supply values to the context is similar to what I explained in the previous slides. The code for using this is also not much different aside from the terminology. Since there's no significant difference in how it's used compared to what I've just explained, I'll briefly show you the code. We've now gone over the main components commonly used in Declarative UI. I hope you noticed that aside from the differences in the programming language used by each UI library or framework, there's not much difference in how they are actually used. By understanding the broader perspective of Declarative UI, you'll be able to quickly adapt to other Declarative UI libraries without much difficulty. Last but not least, let's take a look at the evolution of UI state management, starting with React, which was first adopter of the Declarative UI paradigm. I assume that those familiar with React or React Native already have some knowledge in this area. Now, I'd like to discuss how the state management architecture and paradigm could evolve in Compose and SwiftUI. I'm not sure about Japan, but in Korea, the MVI and TCA architectures are receiving a lot of attention. To briefly explain MVI or TCA architectures for those unfamiliar, user actions are sent to state store, where the store processes the actions according to internal logic and updates its state. When a view subscribes to the store detects a state change, it updates the UI accordingly. Many people prefer these architectures because they manage UI state by storing in a single store and updating only the values in the store. It can enhance the stability of UI state management. But frankly speaking, it might have gained even more attention because it is often listed as a requirement in job postings. Then, I can give a question for this. Is this really the latest and hottest technology? In fact, the concepts used in MVI and TCA have long been present in Flux architecture and Redux pattern introduced by React. If you look at how Redux is treated in the current React ecosystem, it might come as a bit of surprise to the native mobile developers. Nowadays, many React developers have a strong aversion to using Redux. One of the main reasons is the excessive amount of boilerplate code required. It makes it inconvenient to constantly switch between multiple files to just build a single screen. Additionally, the process of fetching and updating the state involves writing a significant amount of code manually, which adds to the discomfort of using Redux. You might relate to this as well. So let me give you a typical example. Just imagine you are trying to implement a like button for a community app. First, you change the state and keep it if the server request succeeds, but roll it back if it fails. Thinking through and implementing such a feature likely involved a lot of effort and an overwhelming amount of boilerplate. In response to these challenges, React community has introduced a new concept for state management called async state management. Before diving into async state management, I'd like to briefly introduce SWR concept based off what I'll explain. SWR stands for stale while revalidate, a strategy that allows a service to use existing cached data while fetching new data from the server. By handling data using the SWR strategy, you won't need to spend much effort managing API response caching. Additionally, since the strategy can be adjusted with tailored options variables to your service, you can manage API requests and response more efficiently. Now, let's return to explaining async state management. In async state management, data requested from external sources like a server, can be cached and managed according to the SWR strategy. Additionally, based on the data fetching status, the UI can display loading, success, and failure states, relieving developers from the need to manually create variables to handle these states. One example of a feature that can be easily implemented with this state management approach is optimistic updates that I said before, slide's example. Optimistic updates assume that the server will respond successfully, allowing the UI to be updated in advance and only rolling back to the UI to its original state if the request fails. The most well-known library that supports async state management is Tensor React Query. With React Query, optimistic updates are handled seamlessly. RectQuery offers a variety of features, and I'd like to highlight some elements that you might find particularly attractive. First, the most noticeable feature is that the library handles state transitions based on the API response for you. With RectQuery, you don't have to manually create or manage loading or error state. Additionally, caching can be done based on specific keys that you give. The first parameter of useQuery can be considered as a key for the asynchronous request. If you match the caching key to the URL path, RectQuery will cache all responses received from requests made to that URL. Based on the stale time, RectQuery will return the cached response if a request made within that time frame. And after that, it will send a new request to the API and return the updated data. Lastly, regardless of the stale time, you can forcibly invalidate the data map to a specific cache key based on the situation, allowing you to fetch new response data. In this code, the invalidate Lambda function will be a good example for this. Now, I'd like to wrap up this session. Let me quickly summarize what we've covered today. First and foremost, the key takeaway I want you to remember is that the concept of declarative UI is not tied to any specific library and can be applied anywhere. This means that once you understand these concepts, you'll be able to read or work with codes from libraries you are not even using. As for a tip, when studying declarative UI, I recommend looking into the methodologies used by React developers. They've been grappling with the same challenges the Android developer like us face today, only several years earlier. If you can adapt their solutions to fit Android or iOS, I am confident you will be able to master declarative UI more quickly. Okay, that's all I have to say. Thanks for all participating in this session. Thank you.